So good morning, everyone. Welcome to this second lecture in the series about Earth systems modeling. And this morning we are really very happy to have Robert Maisha with us. I hope, Robert, I pronounced your surname correctly, of the South African Weather Service. Great. He's a colleague of Mary-Jane Bopape that you met 2 days ago. And Robert today will start introducing us in the nitty-gritty of the modeling. Yeah. So Robert, you're already sharing your screen. Maybe you want to press the button for the full screen view. That would be probably better for readability. And then you're welcome to start, Robert. And maybe it could be interesting for our participants to hear a brief introduction of yourself so that they know who you are. And then, as we discussed previously, you're most than welcome to close your screen if your video if you're worried about connectivity issues. Yeah. So, Robert, please, over to you.
Yes, good morning, colleagues, and good morning to our hosts, Francisco and Krishna. Yes, my name is Robert Maisha. I'm a lead scientist in data assimilation in the South African Weather Service in the Research and Development Department. Yeah, I understand you didn't get my CV. I've got a master's in meteorology from the University of Pretoria and an honors degree in meteorology and also an honors degree in applied mathematics. So I've been working with various models. The first model that I worked with was the WAF model. I know most of you should know the WAF. Then I moved to that is when I was at the University of Pretoria. And then I moved to the CSIR, and then I was introduced to CChem by Dr. Mary-Jane Bopape and Professor Francois Engelbrecht. So I've applied the WAF model, the CChem model for NLP and also for climate projection and also urban climate modeling. The other model that I work with is the unified model, but I'm working on a data assimilation concept. That also goes to the WAF model. I also look at data assimilation. So I'm going to switch off the video and then start sharing the presentation just so that I don't waste a lot of time.
Thank you, Robert. Thank you very much.
Did I switch it? Yeah, I switch it off now. Yes, yeah. So I'm going to start sharing. Yes, so I'm going to introduce you to the CChem model. And I understand there are various ways of doing this, but I'm trying to figure out what is best, whether I should do the presentation first, and then I'll go and do the practical, because that is what most of you will need to know. So I'll start with my presentation. Yes, at source, we are running the CChem model at NLP timescale. And of course, in the past, I've used the model for climate projection and also for urban climate modeling. The CChem model has been developed at the CSIRO. CSIRO is the sister company to our own CSIR. So CSIRO is the Australian one. So the model is fully non-hydrostatic, and then you apply semi-explicit and semi-Lagrangian dynamical course. So it allows you to adjust your time step as you wish. And then this model has so many applications. You can use it in NLP, you can use it in regional climate modeling, and also to urban climate modeling. And some also use the model for air quality modeling. So I'm going to explain the usage of the CChem on NLP and also the climate projection up to urban scale modeling. But I won't touch on the usage of CChem on for seasonal prediction. But yes, you can use the model for seasonal prediction once you have the skills to do so. So if you are interested in the CChem, you will see there are so many publications that comes. You got McGregor, John McGregor is the one who come up with the model, and then you've got Professor Engelbrecht. They used the model for so many years, and so many others. So this model support for weather forecasting, climate, and urban climate modeling. So we at source, we want to use the model for daily weather forecasting and also for research and also to support the PhD postgraduate students from honors, masters, and PhD. And then the system is also being applied. It also various institutions, the CSIR where I worked in the past, they're using that, and yet source and also at VETS, you know. So the first thing would, the first thing would be to download the CAM. Sorry, it's CAM, it's not CAM. So for you to download the model, you have to go into the CAM Confluence, which is the web page. I don't know, where can I find the highlighter? Pointer option. So I'm gonna use the pen. So you can see the source code, you can download it from the CAM Confluence, which is the web page. And then you go into the Bitbucket. You will see that the code is made out of various components. You have got the teraid for the terrain, IGBP veg. You can see this is veg, SIP veg, ocean bathymetry, the CASA field, which is the carbon, CDF VIDA, this one does your mathematics, and then Aeromis has to do with the aerosols and the code itself, and PCC to HIST. I think I didn't include the component for the air quality. It's called the CAM TAPAM. That is where you do your air quality modeling. So on the Confluence web page, I will show you once I finish this presentation. When we try to do the hands-on, you will see that there is something called run CAM, and then all these components are actually explained and how you use them. And then also I will show you how to install maybe one component, and then for the rest of the components, when you have time, you can email me, and then I'll assist you in, if you are using the CHPC, and then I can show you where the code is, and then you can just run. But if you're not on the CHPC, then I can help where I can, but you need the MPI, the NetCDF, and also this Fortran compiler. It can be G-Fortran, it can be Intel, it can be Cray. So, but I'm more familiar with the Intel one. So I'll explain when I finish the presentation, and then I'll show you how to do this hands-on. And then on this screen, you can see on the web page where you can actually download. So the source code is available to the public, it's free. And then when you are on the web page, shows you where the master is. And then if you just click the download, and then you can download the code with all the Fortran programs, because the model is made up of Fortran programs, and then it runs the model. So all those models will be compiled in once. So you don't have to compile all of them if it's a CAM. So once you have your code, you will have to create the directory. So on the CAM webpage, it tells you must have a directory called CAM install. So in this case, in the CAM install, you have your source code. The model needs the GCMCCSSTs to run, and then you will have your scripts. You can have your CMIP directory where you can put your CMIP 5 or CMIP 6, and then you can also use your array data or ERA 5. But I'm not sure. I haven't tested with ERA 5, but I know with array you can run the model from 1979 up to 2017 for your climate studies, which is not a problem. And then you have something called CAM data, where I will show you what you find on the CAM data. And then you have got your vegging, all your vegetation components, and then standard input, and then cable, use this one for land to couple the CAM with the surface parameters. And then, yeah, that is for the screen on the left. On the right, here, when you have a directory called source code, for instance, and then I've got source code January 2022, probably that is where I wanted to do some compiling, but because of time, I haven't done all the compiling of the code, but I can show you. So here, you compile the Aeromis, the CASA field, the CAM, and you can see the TAPAMX. For those who are interested in air quality modeling, yes, you can run your CAM, and then you take the app from the CAM, and then you feed it to your TAPAM model, and then you run your air pollution model. So that is the nice thing about the model. CDVAR, that is where you do your mathematics. It does the mathematics basically for you when it does pre-processing, put everything into perspective for you. And then G2N, it convert the GRIP files to NetCDF because the global observations that we have, the GFS data are in GRIP files. So this code will convert that output into NetCDF for your input to the CCAM. IGBP veg, it does the IGBP, which is the vegetation component. For those who have worked with GIS, you know about this, where you do your classifications of the land cover, the topography, and all those. And then here you have your ocean bath, but I'm not gonna explain all. Like one, I'm not gonna explain ocean bath. These are the bathymetry of the oceans around the country or anywhere where you want to run it. The nice thing about when you run the CCAM on NLP timescale, does PCC twist for you. So that means when it's finished running the model, it does the post-processing. All you have to do is to plot the output. And then QSPLIS, you know, this is mathematics. And there you will find that it puts all the scripts for you, the vegetation, the terrain, and the VPR. So all these components. So the first thing that we'll do will be to when you download the code, you unzip it. It's either use gzip. If the file type you find it's a tar.gz, you can use gzip or you can use scanzip. And then after that, you say tar as xvf if you want to enter the file. So the CCAM code will come in a gz, and then you can also scanzip it. And then when you navigate through the source code, you will do your edits. I will show you how to do the edits. And then after that, on the make file, and then you do what you do to configure the model. You type make. Make goes with the Intel compiler. If it's a G4 compiler, that means it will be a gmake. And then after it has done all the compiling, and then it creates something called a globp, which is the executable. And then all those executables that you create, you can see here, Aeromis, so all this, so basically it takes a day to compile the code. And then once you have compiled the code, you put it in a bin. You know what, we all know what is a bin. So in a bin, you put all your source code. That is where you point your script to when you start running the model. So in this case, I'm just showing you what kind of data you find. One is GCM SST, and then you find all those RCP data, which is, those are the SST's data. And then in error, you find the error in trim. And then in CCAM data, those agent V, it has to do with the models in the model. If you are running the models with 35 vertical levels, this agent will be 35. If you are running with 80, it will be 80 here. And then Virgin, you find topography info. In standard input, you get your CO2 input, and then you also get your ozone data. So now let's look at NLP, because when I finish here, and then I'm going to show you how to do it, because I don't want to mix things, because it's going to take time. So it's better if I explain this, and then we can go and do the code itself. So for NLP modeling, the first thing is, once you have got the code, you download your GFS data. The nice thing is on the web page, I'll show you which web page, you get your script. This script allows you to download the data that you want. The nice thing about this CCAM is it's a global model. So when you're running a global model, you only need one input file. So the model itself, you run with the one input files, and then it does the global configuration. And then when you start to nest, then it does your regional configurations. And then with the regional configurations, and then it starts to create the boundary conditions for you. And then it starts integrating forward. If you want the forecast for 48 hours, it will allow you to do 48. If you want 72 hours, it will allow you to do that. So you decide what you want to do. So here, I'm showing you the UCA web page where the GFS data is archived. And then you will see that here we're using GFS, NSEP GFS 0.25. These are bias corrected, and you will see the analysis there, and then you've got various data sets that you can download. It depends on what you want. And then here, I'm just showing you that if you want to do your past case studies, this is like when you want to run maybe cases from, let's say 2000 up to last month, the data will be on this website. So then you will use the script. The script allows you to do all the download. But if you want to do operational runs like today, I'll show you the CCAM as it's running. Here, I'm just showing you the data for the 15th of February. And then if you want to do the 00 Zulu cycle, you'll go 00. If you want to do the 06, you go 06. If you want to do 12, then, or you want to do 18. So if you're interested in running the model operationally 4 times a day, it gives you that opportunity to run it 4 times a day. So if you are looking at today, the data for 00, it's already there. If I look at now, the time is, it's 09 minus 2, it's 07 Zulu. So that means the 06 Zulu data for today is already available, but the 12 Zulu is not there and the 18 Zulu is not there. So here you will see the analysis. So when I download, I'll download only this file. If I'm running the 00 cycle, I'll go and download gfs.00 PGRB2. These are the bias corrected analysis according to my understanding. So the nice thing about this is you get to create your own script. That is the nice thing about working on Linux. You get to create your own script where you put your date. I don't know why it's getting, maybe I made a mess out of it. You have your date, and then you have your directory where you put your UCAR script, and then you will say, okay, I want to download the first one. And then your script, this is for operational. This script will go into the UCAR web page. You can see the UCAR web page and look for the data, the 00 that I show you, and then it goes and look for Atmos, because some will be running the wave models. So I think if I go back, yeah, you can see prod. Here I show Atmos, but you can also find data for the wave model. So then it will download the file for you. Once you have downloaded the file, this script will download one file in 40 seconds, and then you've got your file. The next step will be convert your grep file data to NetCDF. Like I show you, there is a code called G2N. So with that, you have to take the GFS data and you put it in a data format that the model will be able to read, or the code to convert, which is proc GFS to NetCDF. It needs this type of file to convert. So here you will decide how many grid points you want. So in this case, I decided that I need 288 grid points in the X and 288 in the X and the Y. So then I said, okay, I put my center long at 27, which is, that means I'm interested in Southern Africa. And then I put my center lat at minus 19 degrees south. This is for SADC. I call it SADC domain. And because my GFS data is coming at a 0.25 resolution, I'm not going to change anything. I said, okay, I'm taking the global data, and then I'm putting it in a region, which is SADC, and then I put the resolution at 0.25 as the data is at the resolution of 0.25. And then I tell the code where the G2N file is. And then there is my G2N. I have various ones. So from then, it will go and run its own commands, because this is a .csh script. People are familiar with Linux, you know that you have got a bash, you have got CSH, it depends on how your machine is configured. And then what does G2N does? It looks at the QSPLIS, then it tells you that it's gonna put some output levels in pressure, or in pressure levels, or GPM levels, and then it will tell you that if you have to do the inversion, it's gonna do that. And then it tells you what the Q-split is looking at, and then it takes all the height, the temperature, U grid winds, V winds, RH temperature, this is TMPO, so it's a repeat, PMSL, AGT, all these variables, and then it will put new variables that the model will read, and then it will run the G2N, and then it convert the data for you. Once it does that, it will create the GFS, because immediately here when you run it, the output will be GFS dot, it puts a date, and then it will be a NetCDF file. Then the CChem needs to run the NetCDF file. So once you have got your data ready for the CChem, the script that runs the model, it's a big script, then it will take time for you to understand it. And then it tells you that, okay, if you look at the events that you are interested in, you know it uses mathematics. Speed is equals to distance over time. So if you want to capture the events that are synoptic scale, it means that you can use a synoptic scale. Your resolution can go up to 60 kilometers and your DT should be 1,200 seconds. But for me, and for operational purpose, my interest will be on something that is at 4 kilometer resolution. This is what we call a convective permitting scale. So DT should be around 60 seconds to 80 seconds. So here, I normally use 60 seconds for my output. And then the model on the web page, it shows you various resolution and then the grid size, because the model runs on a conformal cubic grid. So in this case, you will see that if you are running on a 32 kilometer by 32, let's say your global model is running at 32 kilometer, the regional one, first regional domain at 6 kilometer, and then the other one at 1 kilometer. So that means you can use a C96 or more. C96 means 96 levels or 96 grid points in the X and 96 grid points in the Y. So at source, because we're running this model operationally, or we are doing the test runs, we're going to get it to run operationally on a daily basis. We are always, or we are interested in anything from C192. So if you want to run urban scale modeling, you will see it does a C1536. So this is very high resolution, and then it's also expensive. So if you are able to afford this, then you can do this. And you also need to have permissions to run this, because on the CHPC, you can go into large queue or normal queue or shared queue. So if you are on the large queue, yes, you can run at this resolution. So these are the grid size and output domain. So if you go to the CChem webpage, you will see all this information. So now the script that I run, it's a .sh script. So in this case, I said, okay, I'm running a .c576, meaning 576 grid points. Here I was just using a handcast, and then I said, okay, the first domain, which is from the regional or from the global, will be at 9 kilometers, and then I go to 4.5. 9 kilometers over SADC, 4.5 over South Africa, sorry, 9 kilometers regional, and then 4.5 kilometers over SADC. So for South Africa, we always go for 1.5 kilometers. So this script allows you to set the date, the month, and the day, and then it will run the PBS script. The PBS script is the one that will do the submission for you. So on the PBS script, because we are using the CHPC resources, first thing, they will give you something like 64 nodes or more. So for me, I've got 72 nodes, and then for each processor has got 24. So if you say 64 by 24, you will see it goes to something like, I think it's 1,576 or less. So you can do the mathematics. And then I asked to run the model for at least 12 hours sometimes. But for operational purpose, I want this output within an hour. And then they set up that I run the model. This is for my PI. I know you listened to the presentation by Dr. Upape. So this is the group. So there are various groups depending on where you are. If you are at the CSR, they will give you a PI. At VETS, it's a PI. In all these institutions have got PIs. PI means principal investigators. So you will fall under one PI so that you have one account for the institution, or you can have 2 or 3 PI, it doesn't matter. So now for you to run the model for operational purpose, you must be on the large queue. And then you can tell it where the central latitude and central log is. And then you can say, okay, for the the first domain, which will be your global one, you can say the size is C576, which means 576 grid points in the X, and another 567 in the 576 in the Y. And then for grid size number 2, which is your other domain, the nest, then you can go for 504. And then the number of processors that you can use for the day, you can go up to 1,536. But for me, I take this or I take less depending on whether I want to use the model. The nice thing about it is when you go and take 1726, your model will be faster. And then others can use the resources after you have used them. So that is the nice thing about it. So when you do the setup, you can look at the radiation, the cloud, the microphysics, the boundary layer scheme, all the stuff you put there. And then when you're done, you can just go and run the model. And then the nice thing is the CCAM will post-process the data for you. You don't have to do that. And then you can see I'm just showing you in the result. I've got a CCAM at 25 kilometer and then 4.5. If you want to see what is on there, you can do NetCDF. But firstly, you must run your bash script that activate the NetCDF for you. So here's just an example of the output. So that is the nice thing. So at least we still have an hour, and then I will show you how to do most of the stuff. And then also one thing for climate projection, you need to set up your cable, the CCAM data, like I explained. So the model is, you have got one model that does so many things. It can do NLP, it can do climate projection, it can do urban scale modeling, and then it can do air quality modeling. So for climate projection, you have to couple the CCAM to cable. The cable is the the surface model. So in this case, I was using under Virgin. I work with the SA land cover for 2013. And then I've got because I was using also for urban climate modeling, I've got these files that I have to edit so that the model can take all those inputs. So this is the South African land cover for 2013. I know there is one for 2018, which is a better resolution. So this allows you to know where the urban areas are and what kind of land cover you have. And then here, I didn't get the cable, the depiction of cable, but I got the depiction of JOES. JOES is another land cover model. So they do almost the same. They are different. This one is for the UK Met Office. Cable is from Australia. So this model, this land surface model, they do almost the same thing, but they differ a little bit. So when you're running the CCAM at climate time scale, firstly, you have to run it. If you are running with error data, you have to put it on a grid of 50 kilometer first, and then you have to go to 8 kilometer for your own climate projection, and then you look at the various area of your interest. But I won't set up this cable for you, but it's better that I explain so that you know, just in case you want to run the CCAM for climate projection, then I can assist you in this regard. So with error reanalysis data, then you can run it from 1979 to 2017. You can do your current climate projection, and the data is there you can see the data is here on a CCAM web page. You can just download it. So you run it at 50, and then you You go down to 8 kilometer, and then you do the post-processing separately for the variables that you're interested in. For urban climate modeling, you use the same model, but then now you include your urban parameters. What are the building heights? What are the heights to width ratio? This is when you go to straight. It's like you're running model on a street now in a city, and then you can look at your albedo, your emissions, and all the stuff. So then when you set up the cable also, it's like when you start with 50, if you're doing error, and then you go to 8, and then you go 1 kilometer. But if you're using CMIP 5, RCP 4.5, 8.5, the data is already at 50 kilometer resolution, so you don't have to rerun the model at 50. You just go and run it at 8 kilometer, probably over South Africa or over the select, and then over the city of your interest. So now, for urban climate modeling and all other models, then it shows you what parameters are there. And then here, I'm just showing you that you can use the CMIP 5. You can use any data that you have. And then here, it shows you all the variables that you may be interested in. I put in this because some people will say, what are the variables of interest? So you have got so many of these variables. So I'm not going to talk about the air quality ones, but yes, the CCAM model, you can run the CCAM, and then once you finish running the CCAM at 1 kilometer, and then you can feed into the TAPA model, and you can do your air quality or your dispersion model. So that the CCAM allows you to do that. So now, that is all that I needed to present on that is the introduction. So for the next, because I still have an hour, I can then show you how to actually do the competition. But I think I can allow for 1 or 2 questions just instead of just feeding you with all this information. And Francesco?
I think Francesco might still be in his meeting. But guys, y'all are welcome to ask questions in the chat, or if you have a question you want to ask, you can just raise your hand and then I'll ask you to unmute or whatever. So I'll give you a few minutes just to ask some questions before Robert continues with the next part. There were a few earlier, Robert, but I've answered them already. So.
Sorry?
There was a few questions about whether people, someone wanted to know if they can run this to test how it works. So Mteto did mention that they will be installing CCAM on the CHPC for any user to make use of.
Yes, on the CHPC, I'm running the CCAM on the CHPC. I've done that for the last 5 years. So yes, the CHPC allows you to run the CCAM, and it's very easy on the CHPC. You can do anything with it on the CHPC. The libraries are well set. You can just go and run. All you need is you go to the CCAM Confluence webpage and download the code and download the data, and then I'll show you where the data is and where the code is. I've already shown that, but if you struggle, then I can assist.
And I believe the CHPC colleagues are also going to try and make a module for CCAM so that it'll be easy for people to just load it.
Basically, they've already put the models, all the models are there. So for me, it was also very, very easy.
Okay. All right, guys, I'm not seeing any questions. Oh, okay, I see a hand. Otto, you can unmute.
Hello.
Yes, Otto.
I have a question around have you seen trends where around specific geographic locations, the effect of like human civilization on the weather? So like, for example, if you think about a large metropolitan area like Shenzhen in like southern China, is there evidence like where you see, I don't know if it's maybe not necessarily pollution, but the fact that there might be very little vegetation in a large square kilometer area because of human development. Or maybe the tri-state area in the US, although that's a little larger. So have you seen things like that where sort of human civilization, not by effect of climate change, but by even vegetation, what's happening on the ground actually affects the weather?
Yeah, I'll thank you, Otto, for the question. I will answer that because I'm doing my PhD on urban scale modeling. So what I did was, firstly, I ran the CCAM with error data from 50 kilometer, then I went to 8 kilometer, and then I went to 1 kilometer. But my studies is focusing on a city of eThekwini, which is to the east coast of South Africa. What I've seen for both error data and CMIP 5, RCP 8.5, with the land cover, it will show you where there is high vegetation and then where there is low vegetation, and also the city. The nice thing is when you update your land cover data on the CCAM, it will also show you monthly variation in land cover. Like when it's summer, you've got very high vegetation, and then when you get to, because of the rain, but when you get to winter, you'll see the vegetation starts to decrease. Yes, I'm modeling urban heat islands. I have set up the model with the urban parameters for the eThekwini, the building heights, the road emissions, industrial emission, all the albedos. So I think on the last slide, I show you the impact of that land cover. Yes, the simulations that I've done shows that when you are within the city, you will get your urban heat islands, and mostly in summer. Why? Because of course, the short radiation is the same. Short wave radiation is the same, but the outgoing long wave radiation will get reduced because when you have your buildings and then you have got your artificial surfaces, it absorbs more of the shortwave radiation, and then it's stored in buildings. But because of less water bodies, you will get your urban heat islands, and then you'll see that the temperature within the cities, they are high. The boundary layer within the city is disturbed. You look at also the urban fraction. So in this case, I was looking at the urban fraction of more than 90%. So meaning the entire city of eThekwini was mostly urban. Yes, I have done the projection up to 2099, and I have seen that yes, the UHI for that area is increasing, although we have got climate change. But of course, we already have greenhouse gases in the atmosphere. So now, the combination of urbanization and also greenhouse gases will result in the increase in temperatures and then also your climate change. So yes, it was a very good question.
Okay, we have another question by
Bashiru. It's
Bashiru. Yeah.
Yes, my question is, what informed your decisions in selecting the parameters? The model parameters. How do you select those parameters? What informed your decision in making those selections from the model? Thank you.
Okay. Thank you, Bashiru. For urban scale modeling, the parameters, the first one will be the land cover. The land cover, you need the latest. So that land cover will have different land cover classification and vegetation type, and water bodies and your cities. So those are real parameters as they are. The next step for urban climate modeling is your measured urban parameters. Measured urban parameters means you measure those by LiDAR, and then you also collect the emissions from the road. You measure the building heights to width fraction, the road fractions, and all those things. So it's not about how you choose them. It's about what is available. If those parameters are available and you can measure them, the CCAM itself allows you to use measured urban parameters as you read them, as you can see them. Like when we're running the weather model, for the analysis, we use the most recent available observation as they are read by our AWSs. Also, a very nice question, Bashiro.
Thank you.
Okay, Robert, I don't see any other questions in the chat or no one else's hands, but, oh, wait, there's a hand. Floyd.
Floyd.
Yes, good morning. I wanted to ask, actually, it's more or less like, it's not really similar, but then it's on that aspect, because I'm doing some work on heat waves, and we are trying to maybe like try to find out if they may be like some possible cold waves that might happen in the future. So based on it, because I've not yet been exposed to such a platform, which is a good thing that now I've seen, is it actually possible to actually run simulations that could tell us like what would happen in the next 10, 15, 20 years and all of that? And then also on top of that, like, then what variables should we consider when we are looking at heat waves and cold waves?
Okay, thank you, Floyd. Yeah, so what happened is, like I was explaining, with the error data, you can run your current climate. With your RCP data, RCP 4.5, 8.5, meaning CMIP 5 and CMIP 6, you can do your current projection, and also you can do your future projection. So what do you need? It depends on what you're interested in. If let's say you're interested in heat waves or cold weather events, you can run your model at 8 kilometers. But if you're interested in what is going on within the city, that is when you go to, it's either you go to 1 kilometer or you go to 0.333 meters. So then the parameters will tell you, if you are looking at heat waves, of course, it will be temperatures. And then I remember when you do heat waves, you use your Clausius-Clapeyron's equation. I think there are some publications on that. For an instance, I'll make a reference. We did heat waves over the city of Joburg. So if you Google heat waves over Joburg, then you'll see we did some climate projection. I think it's up to from now 2000, I think up to 2099. We extract the temperature data and other variables that you need, your relative humidity that shows you the moisture. So there are various there are many variables you can look at, and then you can all you have to do first is do some literature study, and then do also literature, see what has been done with CCAM and where. Like in China, and the CCAM has also been applied in a tropical settings like Singapore and all those other countries. So the most important thing is you do some literature study. What do I want to study? What resolution? And then what are the parameters? Then it will tell you. If it has to do with temperatures, you look at various temperatures. You have got T-screen, which is the screen temperature. You have got surface temperatures. So surface temperatures will show you the diurnal cycle. And then you will tell if there is a heat wave or the UHI heat wave. You have to define it in terms of how many days of very high temperatures when compared to climate. So there are so many things you can do. And the variables themselves, they will guide you. I think I still have there is another question by Bashiro.
A follow-up question.
Yeah.
Just as you were trying to do some slight comparison between regional climate modeling and the weather modeling, there's always been this argument between the driving forces between these two models. If you can throw some light on the difference between weather modeling and climate modeling, whether regional or global or something. That's all. Thank you very much.
Oh, okay. Okay, firstly, the NLP, which is the numerical weather prediction, that is an initial and boundary condition problem, IC and LBCs. So when you're running weather model, if you're using CCAM, you'll only be interested in your initial conditions for this. But if you are running at boundary conditions, they will provide you the analysis for various emission scenarios, and then how it changes with time. So the nice thing about the models, they can integrate forward in time. But I'm not sure if I'm answering you correctly. Remember, weather is the conditions of the current condition of the atmosphere at a specific point in time. Whereas the climate, you're talking about a period of 10 years, 30 years, but that is an average weather conditions of that area. So the years, they differ a little bit, but because the climate is just the collection of the weather condition over a certain period. Whereas when you're talking about weather, you're talking about now. So you'll see there is a difference when we set up the model for NLP and also for climate projections. And it also depends on climate projections are done by various climate models that have got a global settings. Whereas when we run NLP models, because of their complications, we run it mostly with the regional models or global models. That global models are used to feed into a regional model at that point in time. So if there are not so many questions, I want to show you how to download the data and then how to configure the data. I will just show you one or two things, and also how to run the model, if you allow.
I think you can go ahead, Robert. There doesn't seem to be any other questions.
Okay. So in this case, I have got my machine. Oh, sorry. I don't want to open the mobile external. I've got my machine, and then I log into Lengao. So the first thing is, I don't know if you'll be able to see this one.
It is a bit small. If you go to view on the top of your thingy, on top of mobile external.
Oh yeah, I'll go there. So the
and then you can just zoom in a bit.
Yeah, I'll do that. Can you see this one? Can you see my web page?
No, it's mobile external that's showing on the screen. Right?
Oh, okay, fine. New share. Okay. And then share this one. Can you see my web page now?
Yeah, Firefox. Good.
So here I'm gonna type CCAM Confluence, because this is where I'm gonna start. You can see, I will make it a little bit bigger. This is your CCAM Confluence. It's a CSIRO web page. You can see it. I'm opening that for you.
Yes, it's opening still.
Sorry, it might be the 3G. So you can see the nice thing about the CCAM model. Did I put do I still have a pointer? No, I don't have a pointer here. So you can see the CCAM, and then if you click, you will see getting started. Now I'm on a 3G, maybe it's slower. Getting started, it shows you what you need to do when you're learning about the CCAM. You see there is instruction for installing. There is the code. Can you see the code now? And then here, so you can, if I click on this one, the pit bucket, the pit bucket is where you're gonna download your code. So now, there is the code. So all you have to do is download all of this code. So I'm going to show you how to download this one. You will see if I click on arrow miss, it will open. So let me just show you how to open the CCAM itself. There is the CCAM. I'm opening on the CCAM. Can you see? You can all see there is the CCAM. So it's a very big code. And it's a very nice code made of Fortran programs, but when you compile it, you will just need, there will be a model that does that. So for you to download, you just click on the download thing, just showing you can, and then I say just save file, I save it. So it's gonna save somewhere on my desktop. So if I want to see where I download it, and then I'm gonna show you. So basically you will download all of this code, all of them one by one. And then I wanna go back and show you how to get, this is to download the input file. So if you, there is this, the pit bucket, and then here you have your GCM downscaling from the GCMs. So the first one is the code, the next one is downloading from GCM. So when I open up here, you will see it shows you what is on what you need, everything that you need. And then also it shows about relocatable weather. And then scientific description. So everything that you need to learn about the model itself, it's here. And then software and model configuration. So please don't be scared. You can read anything about the model here, anything that you need to know. So it's all here. And then I'm going back to getting started. And then let me go back to the dashboard. Go back. Just want to show you where you get the data. Yeah, if you go down here, you'll see the scripts, and then you can see. So first thing at the top, you will see the source code. You download the source code, all of it. And then the second thing, it will show you the scripts. These are the scripts that you need to run the CCAM. This is the CCAM data that you need. You open this tab, and then you see what is inside, and then you write your own script. People who work with Linux, they know. You run your own, you compile your own script, and then you can run it, and then you download the data. So I'm gonna show you what is inside Array, just to show you. You can see this is, if you want to run the current climate, this is the data that you can use. From 1979-01 up to 2018-07. But if you want to use the era 5 data, the latest available data, so that means you can contact the CSIRO. You can see here it's created by Marcus Thatcher. So if you contact Marcus Thatcher, then he will be able to assist you with anything that you want to run with the code. So the next thing is, after you have got your code, you go into the, I have got CDCCAM installed. Here you will see CDSRC. This is where I put my source code. You can see the source code, it has got so many years, CD. And then here, this is what I did in September 2021, CD bin. This is in the bin. I'm just showing you that after I compile the code, it goes into the bin and then Terra add. But before it goes there, this is what you need. CD CCAM. I'm going into the directory where you have got my CCAM code here. This is what you have seen on the web page. This is what I've downloaded. But when I downloaded, it was a zip file. So I unzip the file and then do some edits. Where do I do the edits on the CCAM? I say vi make file. Where is my file? So on the CHPC, they will provide you with all this information. This is what you need to run the CCAM. You need your netcdf root, which is already installed on the CHPC. You need also the net ifo type that is already there. HDF5 is there. zlib is there. And then your MPI is there. So you will be asked to edit the NC flex here, whereby it will point to the netcdf and the zlib, all this, and then into the include directory. So when you go down there, you will see that the code is run through the modules. And then you also have your FF flags that you need to set up. And then also you need the libs. And then you have got your code. So when you have all this, you just put them. And it depends on which compiler are you using. So in this case, I run the CChem with iPhone. Do you see common compiler flags? So here, common is the Intel one. So if you are using a G4tran, you will see also there is the PG4tran. You will use the G4tran. So depending on whether you are using a crate compiler, and then you also have to set up the crate compiler, which is the FTN type. So when you have this, when you have the code, just want to show you, you will see there is a glob P there. This is the code that you use to run the CChem. But for you to compile this code, it will take you about 30 to 40 minutes because it's a very big code, because it has to go through all those modules and all those Fortran compiler. So what you need, I'll show you. For those who have been working on the CHPC, what you need is VI on the Lengao. For you to compile any code, you understand, to compile any code, you firstly have to ask for a space. So in this case, I'm gonna do this. I go and say Q sub, and then I said, okay, please give me 1 hour. Under my group, I'm saying, please give me one node, and one node is about 24 processors. And then on my group, 1022, and then I said, please, I need to do this for an hour. So once I enter this, you will see it goes into a jobs something, because you will never be able to finish compiling the code if you didn't ask for the node. You need a node first. So this will take time, and then you get your node, and then that is when you compile. So when you will see, if I say ls minus ltr make star, I've got my make file there. The make file is the one that when you're running the code, you just type make. Like I said, make will call the Intel compiler. So I want to show you, if I say make, you see this, it just break everything, because there are so many things that haven't been sorted out. I don't have the right stuff. So how do I get the right stuff? The right stuff comes from the node there. And then I can say cd CChem install ls minus ltr cd src. SRC is for the source code. This is where the source code are. And then I say CD, I'm just going to go back to that one. Say ls minus ltr. And then I said cd CChem. I just want to show you, this is, the code is there. But if you see, there I type make. When I type make here, everything crashes because it doesn't know what you're doing. But if I'm on the node here, there's still some stuff that auto. Yes. I see a hand up.
Hello. What exactly are you compiling the code first? Maybe I'm not understanding. Maybe it's just different use of terminology. What do you mean by you're compiling that code first?
What I'm saying is this: the code, you download the code as it is, but for you to use on any machine, because the machines are different, you have to customize the code to your machine. Then once you have customized your code to the machine, because you might be using a G4tran compiler, you might be using a Cray compiler, you might be using an Intel compiler. So for each compiler, it has got certain requirements. So for the code to work, it must be configured and compiled first. So now the CCAM, you only do one. Make will configure it for you and compile the code for you. If you have got a Fortran program, remember, Fortran program, you run your Fortran program to check if it works. That is configure. And then after that, you compile the program. I don't know, do you understand that language? Fortran compiler, you configure it. You say, if I've got ls minus ltr star.f90. Can you see the Fortran programs? There are so many of them, but because this is a model, you don't have to configure each one by one. If you have got a Fortran program, you say I just want to remind you, let's say ATEB, because I'm interested in ATEB, minus O, right? And then I say ATEB dot out. You see that? That is when you are trying to you configuring the file. So you can run that command. I'm just giving you an example. You run that command and then you say it's not found. Why? Because I haven't put in the compiling information. So how do I put that? I'll look at my netcd ls minus ltr. We just want to see where my netcdf stuffs are.
Robert, maybe if I can just add to what you're saying here. So for those of you that might be a little confused, if you are on a Windows machine, right, you typically, in order to install a program, you run setup.exe, for example. And then that program gets installed in program files. Here, you have to do this manually. So we're basically doing exactly the same thing when you run make. It builds everything for you and creates one file at the end, which is the actual code that you need to write.
Yes. So in this case, I just want to show you something.
Hi.
I'm
sorry.
Sorry?
So is that like, I just have a question just to sort of understand the compiler thing that he's mentioning. So is this the same thing as every single time I'm running Gaussian, I do set off the internet and it hasn't been installed in CHPC. So I have to first compile it on my own and then only run my files. Is that pretty much what you said?
So,
yes. So basically,
yes.
if I can just quickly add there, Robert. So yes, with Gaussian, I've done the whole process for you. What Robert's doing here is that he's having to compile this himself because they haven't done it on the machine.
So in this case,
okay, all right then. Okay, that makes sense.
You can see I'm running a script called ccam run netcdf bash. So this script will activate when I source it. I'm activating the libraries so that if I run this command, I'm just going to show you. If I run this command, you see, there are so many Fortran code there. All of them, it's Fortran and it's the modus and the output. So in this case, I'm just showing you that I can say itab.f90o.out. But can I do this for thousands of these codes? No. You get my point. I can't do this for all these codes because there are many. So what is the best way of doing it? You're running it through something called vi makefile. So this makefile, you see, this makefile has got all the information, all the compiler information that you need. And with this makefile at the top tail, if I tail minus 10 in the makefile there, can you see all these modules there? There are modules there, they don't, there are so many of them. So I can't run it one by one because it's gonna take a year. So what do? I use a make. So if I type make there, you see, so there is something that is breaking because it's not set up nicely here. You understand? But it doesn't mean it doesn't work. it does work. It's just that here it's not set up nicely. So the first thing is you compile all this code. Once you have finished the compiling of all these codes, you move them to bin, cd bin. So all the everything that is an output, the output from CChem will be called GloP. The output from TeraEd is TeraEd also. So now, once you have this code, you can go and run your model. So now to run the model, I say cd project. Okay, firstly, cd run CChem. I just want to show you here. Here, because I'm running the CChem daily, I've got a script that will go and download the DS file every day. So now, this file, I'm just going to give you an example. Here, if I want to do the 06, because we are past 06, I'm going to show you, I'm just going to change there. And then I said, I want the 06 one. But then I look for other 00. And then here I said, okay, I want, next. Here I want the 06R, and then I make it 6. Next. Here I make, oh, sorry. I make it 6 because I want to download the 06 analysis. And then I said 6 there. Next. I look for 06. Here I'm also looking for 06. So now I've got my 06 input file that I need. From where? From the web page. I'm going to show you this web page. So now that I've got my download script ready, and then I just say bash download 06. Now you can see it connects. Oh, there is an error somewhere. Where is it? F1. It doesn't like it. So there must be something. So I must change 06 to make it 0R0, just to show you, to make it simple for me and for all of us. Just want to see. Okay, let's see if it's going to get the 00001. Yeah, so it says the 00, it's already available because I've downloaded it and put it under my proc. So now there is the data as downloaded as it is. I downloaded it in the morning, and then now I run proc. This proc will take, firstly, I'll take this file and rename it GFS, put in the date, and then I run proc with this data, and then proc will do conversion of this. So I can show you how. I can say cd project. Where did I do that? cd mnt, last 3 groups, ERTH 1022, CChem all, less minus LTR, cd, I'm running this on NLP, ls minus LTR for the time, and then I go to pre-proc, ls minus LTR, and then I go to this date, which is today, and then I say ls minus LTR. So what do I need? I need to run that proc. So if you look here, I'm saying here I've got a script called move. This script called move, it will go and find that file. If this file is there, and then it copies this file to GFS, and then it put date and 00, and then it will run the proc. So in this case, I've already activated the node so that I can run this. So how do I do this? I can remove this file for you so that you can see, and then I clear this, and then I can show you what is in there. And then I can VI this proc. This proc, I said, oh, I want to convert this thing over SADC. And then I say, I need a C288. I can change it. Yeah. 288 means 288 grids in the X, 288 grids in the Y. and then it will go and look for my bin, for the bin, and then the source code, and then it will do whatever I need it to do, and then it will do the conversion. So don't mind the percentage here because I'm on the terminal, on the node. So on the node is not where you're supposed to edit stuff. So here, that file is not there, but all I did, the first step will be CP this file that I'm just showing you, and then you copy it into that format so that the G to N will be able to read that format. So now the next thing is say ls minus ltr, and then you say dot prop. This file, you will see what it does. So it takes the grep file and convert it into a netcdf format into my domain of interest. So I'm using the node and I've sourced my library so that it doesn't struggle. So then it's running. So then the next thing is you can see it create a gfs.nc file. But this gfs.nc file, and then you can see it run the g2n.nml, and then it also gives the log file there. So, but these files, I don't run the model here. So once I've got this file, this is my initial condition. So I will go back and show you where you get this data. This is the data that you use VI download. If I take this, I copy this, and then I paste it on the web page. You can't see my web page now. So now let me show you what is on my web page. On this web page, then I share it, and then I put another terminal there, and then I say I want this data. This data it's located here, and then I open this. Very easy. On a script, the script you tell it to go and open this, and then what do you want from this data? You tell it I want the data for here. It's GFS SSTs and GDAS different data set, but I want GFS. So what is available? You will see when I was trying to run the script at 06, it didn't allow me because the 06 data is not there. So, but I want to show you, if I go 1 day back, I can go 1 day back on the 15th, which is yesterday. And then you can see the 00 is there, 06 is there, 12 is there. Let me just open 18 Zulu data. Here, some people run atmospheric model, some people run wave models. I run atmospheric model. So in the atmospheric model, and then there are so many data sets that you can use. It depends on what your application is and which one are you familiar with. So in this case, I'm interested in the GFS. Here you'll see it's T18 PGRF 0.25 degree 000 analysis, and then it's 483 megabytes. So when you're using Linux, you don't want to go and open this data. You see that you don't want to download it that way. Let's see if I can download it that way, but that is not how we do that. We do it through the screen, the script. So that is why I go back to that script. You see the script, can you see it? So
no, you're not sharing. You're not sharing.
I didn't share it. Okay, fine. Let me share. Yeah, I'm sharing the screen now, and then I share it. So you see, so you write a simple script that will go and find it's check if this data is there, and then if it's not, then go and download it, and then you download. If you don't have it in your machine, download it. You download, and then you try. If sometimes some people say minus 10 times, and then you have the data. So now it's because of the time here. This is the directory where I run the stuff. So the first thing because I automated my stuff, I said, okay, the first thing is I'm going to write a download script. It download it. Once it download it, and then it move it. Here it's taking the GFS data and convert it to netcdf because CChem runs on the netcdf file. So the first one, the download, I do it in 40 seconds. The second one, I do it in 10 seconds. So if I just run download, like I've shown you, I just say bash, download. I just want to show you, you see it says the file is already available. So if I say bash and then I say bash, move it. Here I'm just running it and then preparing it for you. So already, although that I show you manually, I'm showing you again that within the first one, I do it in 40 seconds. This one, I give it 30 seconds or 40 seconds or 1 minute to prepare the proc for me. So once I have prepared it, and then you can see it's a done deal. And then I said, okay, fine. This thing it's available. And then if you want to look at it, I move it to analysis. Sorry. So just to show you, I moved this file to a directory called analysis. Analysis is where I put all my data. So all my data, when I run the model on a daily basis, I put them on this analysis direction. So then third step will be to run the model. So how do I run the model? I say I've got a script that runs CHPC daily. So this script firstly will source the NetCDF. The reason why I have this NetCDF file is because sometimes I'm running WAF, sometimes I'm running CHPC. So the requirements for WAF and the requirements for CHPC are always different. So that is why when I'm running CHPC, I activated the libraries for CHPC. When I'm running WAF, I activate the libraries for WAF. So in this case, it will go to say CHPC directory is this one. So then I go there, and then I want C72. And then I go there, then I go there, CD, that directory, and then ls minus LTR. This is where I've been running my model. The model I ran today, and then it started at around 7, and then by 9 o'clock, it was finished. You can see there, it tells me, okay, wait a minute, today, oh, no. Q state minus U. Is it still running or is it failed? So it's still, it's on the queue. So there is a problem on the queue. My model hasn't finished because it hasn't started. It has been put on the queue. And then you can see here, I asked for the 6 nodes because at the CHPC, they allocated me 72 nodes, but I asked now, because they gave me the 72, I'm using 36. So I can even kill this model because it's not running, but I'll show you what I'm gonna do. So here, I've got various scripts. I've got a C72 hindcast. So this script, it's C72, C672, and then it runs the first one at 25 kilometer. And then this is more like the global model. And then I set it up to run the SADC domain at 4.5 kilometer, and then also 1.5 kilometer. Guys, can you see this? Because it's very important.
Yes, we can see it clearly. Thank you.
Okay, so now I open the script. This is the script. Firstly, it will source. Sometimes I struggle with my libraries. Some are not opening, maybe sometimes there are issues. So I source various NetCDF stuff. So then I put the dates the way I want it in this script. And then it will look at my input data. AVN file is the input data. And then I say my input data is under NLP script analysis. I've shown you this for today. So if I do this, ls minus LTR. So you can see this is the file that I'm supposed to run the CHPC with, but because of the queuing system, I don't know what is it because I haven't read my email, whether there are issues in Cape Town, then that is why my model is on the queue. It hasn't started running. Or it's
Sorry,
because,
Robert,
yes.
just to say, yes, there is an issue. We're having a problem with one of our chillers. So the 8 nodes are currently down.
Yes, the chiller. Sorry, thanks. I haven't checked my email because I was preparing for this session. So at least if there was no issues with the chillers, the model would have started running by now. So in this case, when you view the script, this is the script that will do the date, and then it will go and do the code. So in the last 20 minutes, I just want to show you 10 minutes, I want to show you what is this code is all about. So in the code, this is the code that actually runs. I'm going to open it. So this is the PBS script, because on the CHPC, we run everything through PBS name. So in this case, you provide this information. I'm running with 36 times 24, which is something like 800 and something nodes. And then I say, I want to run it for, at least give me a chance to run this for like within 10 hours. And then I'm on the large queue, and then I'm on this group, and then I want you to run the output on this directory. And then here, because of the time, and then I'm saying, okay, longitude 25 degrees east, latitude 26 degrees south, sorry, east south, because I'm interested in SADC region. And then here I said, okay, I don't want to use so many grid points for my global configuration, which is at 25 kilometer. So that will be 25 kilometer by 168 grid points. And then I said, okay, for SADC domain, I want to run it with C672. And then I asked for 864 processors so that the model can run faster. And then when it's finished, others can use the resources. If I take maybe 400, that means my model will run longer, and some other people will want to use the processors that are not available. So it's better to put more processors and do your task within a short period of time. And then when you're done, you give others the processors. So you can see the radiation schemes, everything that you need to set up. And then I said, okay, because at source, we want to run this model operationally. We're testing it. We want to see whether it's gonna be fit for purpose. We said, okay, we're putting 72 levels on that. But because we are testing it, I said I'm using 864. When we go operational, I'm going to throw all of them 72, which is 1,708, so that it will finish within 1 hour, so that we can give the forecasters their product and the public can get their weather forecast on time, because we are an operational center. So then we said, okay, we want to run this model for 72 hours, so that for the first 6 hours will be spin-off period, and then we can give you forecast for at least 3 days, because we are operational. So all these codes, we set them, and then the working directory, I set it, output directory, I set it, and then analysis, this model will go and look at where the input data is. And then when there is the F bin, this is the 2021 source code. In this bin, you will see all the codes are there, so that the model can run. So then I said, okay, fine, I'm not running with 3 domains, I'm running with 2. But yes, I can run with the parent domain over, let's say, centered over Africa. And then the second domain will be SADC, because we provide SADC with forecast, and then the third domain will be South Africa. So it's just a matter of time. We're still trying to test them on, and all the Terra Ed, the IGB, PVEG, everything we set it up, and then the topography data, everything we set. And then I just want to show you, you will see the model will run everything that we asked for, and then here it starts running the CCAM. And then we tell it to run with the DT. You can see here, if the grid race is about 8 kilometers, then DT is about 120. For 4 kilometer DT is 60 seconds. So that means we are running a very high resolution model, which is for the benefit of the country. So now we can look at the CCAM, we're running it at a resolution of about 0.25. If we're running the bigger domain or the let's say a global or low resolution, we'll go for 60 kilometers. But because we are an operational center, we look at 20 kilometers at least. And then all this stuff gets set up. And then I just want to show you at the bottom there. And then this system will do PCC twist, so that I don't have to go and post-process the data myself. It will go and process the levels. And then I will show you, it's going to go and process all these variables for me. in one. I don't have to touch it, and then it will run the NP, and then the number of processors you have seen, 864, and then it process the data for me. And then here I tell it the first domain will be probably over Southern Africa at 25-kilometer resolution. It will do that for me. And then from then I said, okay, I want, for operational purpose, I want 4.5 kilometer over SADC. And you will see I commented out the 1.5 degree resolution over 1.5 kilometer resolution over South Africa, because we are on the testing phase. But once we go, this model goes operationally, we'll just activate all the domains, and then it will run the model. So if I say, I go back and say Q state minus U, there, you can see it's because of the chillers, the model is not running. So then I don't need the node anymore. And then I quit the node. And then if you go back there, you will see now the model is on the queue. And then I ask for 10 hours maximum. And then I ask for 36 nodes. So it's not running, but what I can do, I can kill it, say queue del, because there's no need for me to keep it on the queue, and then I kill it. And then you can see Q state, and then it's gone. So basically, this is how we run the model. And for me to run the model, if I'm here, and then I just go back, CD run, CChem. I just want to show you how to do that, to put that. It's either I use QSub manually, or I can just say bash CChem. I just want to show you it's gonna still go back into the queue because of the chillers. And then I say Q state minus U. You can see it's just queuing there. But I'll leave it unless you say no, kill it permanently. But I can leave it, and then after, maybe when the chillers are, the problem is solved, and then the model can run in. And then within 2 hours, I'm sure, let me show you how much it takes for us to run this. Although I've got some few minutes. CChem WD. And then I'll look at what happened yesterday on the output for yesterday. So yesterday, I started the model run at about 7. By 7:22, within 20 minutes, probably I had my CChem 25-kilometer resolution. Then after 1.5 hours, from 7:30 to 9 o'clock, the SADC domain was completed. So because of the number of nodes that I was using. So if I increase the number of nodes, if you look here, it took 1.5 hours to complete a 72-hour forecast over SADC. But if I increase the number of nodes from 36 to 72, I'll have half this time, from 90 minutes to 45 minutes. So from 7:22 to 45, it was gonna have finished by 8:20. So I think I'm done, and then I can stop sharing, and then I'll allow for some few questions. I don't know whether the Zoom will just kick us out now. Thanks for your audience.
Sorry, we are not like some of the ESCOM user. We pay our Zoom license. The Zoom won't kick us out. Don't worry. Yeah. No,
okay,
Robert,
no, I thought it was, yes.
Thank you so much. It was really fascinating. Thank you so much. It was great. Yeah, thank you. I see there is a question by Bashiro. Please, Bashiro, you can just start talking. Yeah.
Okay, thank you very much. Thank you very much. Even though we have a very little time to go in depth on your explanation, the scripting, I want to ask, since at a point in time you were saying that you run both WARF and you run the CChem, have you ever done some kind of comparison between the WARF and the CChem on weather scale and on climate scale? I want to know if you've done some bit of comparison, because I'm also working at the operational center, and we run the WARF on weather scale, but we intend to run it on the climate scale. I want to see if you can also give us some recommendation, or you can give us some kind of source of advice whether to run CChem and WARF at the same time, even though we also have some computational deficiency? Thank you very much.
Well, so far, what I can tell you is that I've been, for the CCAM, I've been running CCAM for the last 5 years. The first 3 years I was running CCAM on a climate projection time scale. And then, yes, I did some verification, and then I know it's a very good model. And then I've run the CCAM over the last 2 years as for NLP purpose. We have got somebody who's comparing the the CCAM and the unified model. So I haven't got the results, but probably the papers, look out for the papers from now up to maybe in the next 3 years, because we have got a big project to compare the CCAM, to run the CCAM and to customize the CCAM, look at the physics, the microphysics scheme, the boundary layer schemes, and all those schemes within the CCAM. So in the next 3 years, yes, we'll have a lot of papers and then a lot of verification and validation. When you're talking about CCAM and WAF, I haven't compared them because I remember WAF, I use it like for the last, 12 years now, but it has always been at various institutions and also for various purposes. WAF, I've only used it for NLP time scale computation. You can look at my MSc and other people's studies on WAF. I know it's a very good model. I enjoy WAF more than any other model because that is the one model that to me, it's like I've grown up to work with. For the climate purpose, I haven't used the WAF, but I know there are people there is a WAF code for climate projection, but I haven't used it, but I've seen it is there. The CCAM, the nice thing about CCAM is you only have one code that does everything. That is what you say, this system is a seamless system. So yes, okay. I haven't compared those two.
So from your explanation, if you are using the CCAM, is the same code for NWP and the same code for climate projection?
Yeah, you just set up the code with all the supporting libraries just in once. But of course, they are updates. But the same code, you can run it as at the NLP time scale, the same code, you run it at climate projection time scale. If I have some few minutes and then I can show you. Where is my screen?
You probably have to share it again.
Oh. Yeah, I can just show you how. CD dot. I'm sharing now, Francesco.
Yes. Now we can see it clearly. Thank you.
Yeah, so you can see here CD. I've got projects there. You can see I've got project for Africa 50 kilometer, and then RCP projection 1 kilometer, SA 3 kilometer, and all those stuff. So I'm just gonna show you. I'm gonna go to RCP 1 kilometer, just or no, you're not interested in 1 kilometer resolution. Probably you are interested in a bigger domain. So I'm gonna show you what is on a bigger African domain. So here I'm running CCAM at 50 kilometer over Africa. So I just want to show you I was in the last few moments, I was showing you how to run it on an NLP time scale. Here it's on a climate projection time scale. You can see the setup is the same. The FDIR is almost the same. The NetCDF that I run, the source code is the same. Everything is the same. So the difference is now, when you look at this, I'm saying I have got my indirectly here. The difference between the two is this. When you run CCAM at NLP time scale, it will do the cable automatically for you, and then it just run. But when you run it at a climate time scale, you have to prepare the cable. So the cable is prepared separately. But to run the model, once the cable is prepared, you can see here just taking this error interim data for you to run. And then I want to show you where it takes up the VCA. So the VCA there, that is where you run the cable. So at climate projection, You set up the cable for separately where it does the land cover, the IGBP veg, the ocean bathymetry separately. You prepare it once, and then you use it for and if it's for 50 kilometer, you use it for 50 kilometer. If you set it up at 8 kilometer, you use it at 8 kilometer. But the code, it's exactly the same. You don't change anything. You just point to the code.
Okay.
So those are the different cable. You do it separately.
Okay. All right. Thank you.
Yeah.
Thank you.
Any more question? And yes, guys, if you want to run it, you can email me. I think people have my email address. Otto, it's on.
Otto, please, if you have a question, just ask quickly because I'm starting to get worried about the time. Yeah, please, Otto.
Prof. Engelbrecht mentioned that for the global models, they were trying to aim for 100 kilometers. How is that the same thing that you're doing? Because you've been mentioning running grids of 1 kilometer, 8 kilometers. So I'm sort of confused with mishearing him when he was mentioning he was running global. They were hoping to go for 100 kilometers, or are you just running over a smaller data set?
Let me explain this. Our applications are different, but the code is the same. It's a seamless system. One, you can run it for NLP, for seasonal projection is the same, and then climate projection is the same. So the difference here is, if you look at the first question in science, speed is equals to distance over time. So if the distance, the speed, distance, time. So now if you want to catch the global events, you have to go global resolution. And because the globe is big and the number of grid points are many, that is when you see some of the global models are running at 2.5 degree, which is 250 kilometer by 250 kilometer. So some will go down and say, no, we want to run it, the global model at 100 kilometer by 100 kilometers, which is 1 degree. So it depends on who you want, who is your client, and what you want to run the model for. So for global projection, yes, you can go there. But now these global models are at big operational centers, depending on what they want to do it with. You find that for seasonal forecasting, yes, they can still run it at that resolution, which is 1 degree. But for NLP purpose, which is what we do operationally on a daily purpose, we don't have to run it at that resolution. We run it at very high resolution because probably if it's SADC, the distance, the speed, and the time. You want to provide the public with the output at an hourly time every 1 hour or 30 minutes, you see. So that is why we increase the resolution. And we want you to run it for how long? 72-hour forecast. That is what we do. So you see, for climate projection, is the interest in providing the public with output now? No, it's for research and it's for the other purpose. You want to see how the climate change is impacted by greenhouse gases emission. So that is what makes a difference.
Okay, thank you very much, Robert. That was really an interesting lecture this morning, a nice insight behind the scenes of our weather forecast and climate forecast. Excellent. That was really very nice, enjoyable. Yeah. Robert, thank you very much. I know that the next lecture in this course will be given by another one of your colleagues, and that will be, sorry, if I remember correctly, on, no, when is it? Sorry. Today is Wednesday. It's on Friday. Sorry, sorry. The next one will be on Friday. So, Robert, thank you very much. I see there is a lot of exchanging of email addresses going on in the background. It would be very nice for our participants to engage with you. And thank you so much again for your assistance. Yeah? And I would also like to thank Krishna, who kindly agreed to be the co-host this morning. Thank you very much, Krishna, for that. Yeah. And
Okay, thanks.
Participants, thank you, Robert. We meet again at 2 o'clock. And this afternoon, we will have the second lecture of Professor Janelice on Python-based mathematical proofs. So please join us this afternoon as well. And Robert, thank you very much again to you for your time and for the very interesting lecture this morning. Thank you so much. Thank you.
Thank you. Okay,
thank you.
bye-bye.
We will stay in touch, Robert. Thank you very much.
Bye.